Alright, let's go ahead and work out some problems that involve Stokes' theorem. So our first problem here, we're given a vector field f. We're given a particular curve, where it's actually defined as the boundary of a surface, actually. So boundary of the part of the plane, 3x plus 2y plus z equals 1, that's in the first octant. We want to use Stokes' theorem to find the line integral of this f over that curve. So let's go ahead and actually plot that curve. So actually, well, I guess we're starting with our plane. So 3x plus 2y plus z equals 1. That's this plane here. Now that crosses the axes at different points. So if y and z are both 0, we get an x value of 1/3. When x and z are both equal to 0, we get a y value of 1/2. And when both x and y are equal to 0, we get a z value of 1. If we go ahead and connect those points, we end up getting our curve. There you go. That's our curve that we want to integrate over. Now they did state here that they do want us to do it in a particular direction. So in this case, we want C to be oriented counterclockwise as viewed from above. So if we look at it from above, we want to be going from A to B to C to A. Now, of course, we don't really want to actually have to worry about doing all three parts of this separately. If we had to do the line integral just directly, we'd have to do each line separately, parameterize each line, and then add the results of all those line integrals together. But because we have Stokes' theorem, and we're going around a piece of a surface, then we can actually go ahead and integrate over the surface instead. But we have to integrate the curl. So that's one extra step that we wouldn't have to do before, but it will actually make it a lot easier in the long run. So let's go ahead and take the curl of this f. So of course we're going to take these three components as our third line. We have 1, we have x plus yz, and we have xy minus square root of z. In the middle we have the derivatives with respect to x, y, and z. And then in the top row we have ijk. When we write this out, this I is associated with this 2 by 2 here. Or why did I put x? It should be a z. That's our I component. We need to subtract the j component. That's the one that has derivative with respect to x and 1, and also derivative with respect to z, and xy minus square root of z. Then finally, k is associated with this 2 by 2 here. So we'll have a 1, we'll have an x plus y z. And we'll have our derivatives there. When we go ahead and we go by diagonal, so we'll take the derivative with respect to y of xy minus square root of z. Of course, that's just going to be equal to x. Derivative of x plus yz with respect to z, that's going to be y that we're subtracting. So our I component is x minus y. Here we have the derivative with respect to x of xy minus square root of z. Of course, that's just going to be y. And then the derivative with respect to z of 1, of course, is 0. So we have y times j. Or technically minus y, because we have that negative there. Finally, we have the derivative with respect to x of x plus yz. That's just going to be 1. Minus this derivative is going to be 0. So we end up just having a plus k. So the curl's not too bad looking. In fact, the square roots went away. So we didn't have to worry about any square roots in it at all. Our line integral over c is going to be the surface integral over, well, technically here we have to find a particular surface that works, but they've actually given it to us as this particular plane. This plane is contained between that boundary curve. And so we're just going to integrate over that surface. So the integral over that triangle, basically, of the curl dot ds is going to be the double integral over the triangle, over the triangle in the xy plane. So if we view it from above, we have this triangle down here. That's going to be D, or at least I'm going to call it D for the moment. Now, because we're just going to be looking at this as the graph of the function z equals 1 minus 3x minus 2y, we can go ahead and use the formula where we take minus p times the derivative of this function with respect to x minus q times the derivative of the function with respect to y plus r. And specifically, the p, q, and r that we have here are the p, q, and r for the curl, not for f itself. So the curl of f is pi plus qj plus rk. But I'm using the formula from our last section in order to go ahead and kind of shortcut, not have to take the r sub x and r sub y and take their cross product and all that kind of stuff. So when we integrate over this triangle, so what are our limits going to be? Well, notice here that this line here is actually 3x plus 2y equals 1. If we solve for that, we have the equation that y is equal to 1/2 minus 3/2 x. And then x is going to be going from 0 to the x-intercept here of 1/3. Kind of wish I didn't have any fractions in this one, but what can you do? But we're going to be integrating x from 0 to 1/3 and y from 0 to 1/2 minus 3/2 x. Then we go ahead and put everything in here. Our p is x minus y. So we have a negative x minus y times the derivative of g with respect to x, but that is the derivative of this with respect to x, which is, of course, negative 3. Then we have minus q. Q is negative y. And now we have the derivative of z with respect to y, which is negative 2. Finally, we have plus r. R here is a 1. So you have a plus 1. That's dy dx, keeping the same order that we have over here. I'm going to go ahead and simplify what we have in here. So if you distribute the 3 to the x and the y and kind of combine like terms, actually the 3y that we're going to get here is actually still going to be negative 3y. It'll combine with this negative 2y. So we'll have a 3x minus 5y plus 1. And we just get to do some integration now. So the integral of this with respect to y, because that's what we're doing first, we have 3xy minus 5/2 y squared plus y from 0 to 1/2 minus 3/2 x. We need to go ahead and plug that in. So we'll have, what, 3x times 1/2 minus 3/2 x. We have minus, wait, so I'm getting a little ahead of myself, not to that yet. We'll have a 5/2 1/2 minus 3/2 x squared. And then we have a 1/2 minus 3/2 x. Where we basically just replace all the y's with that form. Now, of course, technically here we do have a 0 on the bottom. We have to subtract the value at 0, but because we like to use 0 to kind of make things easier on ourselves, the 0 there made everything come out to be 0. We don't have to worry about that part. But what we do want to do now is kind of expand everything out. So here we distribute the 3x to both the 1/2 and the minus 3/2 x. So we're going to have an x and we're going to have an x squared with different coefficients. Here we have to square this, and just keep in mind to distribute that negative 5/2, and we combine all the like terms. I'm going to kind of skip all that algebra and write down what I got. So I got a minus 1/8 for the constant term. That actually involved the constant term from here, and it involved the 1/2 that we have here. We also have a 15/4x. So that involved the 1/2 times 3x here. It involved the middle term here, and it also involved the minus 3/2 x from over here. Though actually, since that and that canceled directly, this is actually just going to be the middle term of our square. Finally, we have a minus 81/8 x squared. Mostly because when we square the 3/2 x here, we did get over 4. We had the 2 there. That gave us an over 8. So we got some big numbers going on here. But we're going to integrate this. Obviously, 1/2 becomes a negative 1/2 x. Here the x becomes an x squared, but then we have to divide by that 2. So we have 15/8. And here, when we raise the x squared to an x cubed, the 81 already has a 3 that we can divide out. So we get a minus 27/8. We get to plug in 1/3 and 0. Of course, 0 just gives us 0 again. So really, we're just plugging in the 1/3. So this becomes 8 times 3 becomes a 1/24. Here, we can actually take 15 and divide it by 3 to get a 5 on top, but the other 3 makes a 24 on bottom again. And finally here, 1/3 cubed is actually 1/27, which is what we had on top. So really, we just have a 1/8. Of course, we'll then actually need to multiply the top and bottom to make like terms. So actually, we'll go ahead and turn 1/8 into 3/24. If we combine all those, 5 minus 3 minus 1 gives us a 1. So our curl, the integral of our curl over that surface, which is the same thing as the line integral of f over that boundary, turns out to be 1/24. Moving on to problem 10, it's basically the same instructions here. We want to do the same kind of thing. This time, our curve that we're trying to integrate over is the curve of the intersection of the plane z equals y plus 2 and the cylinder x squared plus y squared equals 1. If we go ahead and plot that thing, so our cylinder just looks like that, and we're looking at the intersection of that with the plane z equals y plus 2. So we end up getting this. It's actually an ellipse. Let's see. Will it give me the intersection of these? It did, but it didn't make it very, very dark. So let's turn up the thickness of that so we can see it a little better. I think it also didn't give me a good color. Yeah. Let's make it black so we can see it better. There we go. Our intersection there is actually an ellipse. And we want to integrate a particular vector field over that ellipse. This vector field here, which isn't too bad of a vector field, not too complicated, but we do want to integrate over that ellipse. But parameterizing the ellipse is probably not the easiest thing. Might still be possible. In fact, I think we could do it if we wanted to. But again, we're wanting to use Stokes' theorem here. We can integrate over the part of the plane that's inside the cylinder instead. Integrate over that surface. Of course, we do need to take the curl. So we are going to take the curl of this thing. That does mean that we're going to have ijk, the derivative with respect to x, y, and z. Then we have 2y, we have xz, and we have x plus y. If we expand that thing out along that first row, just the same way that we did before, here we have xz, here we have x plus y. That's our I component. We have derivatives with respect to x and z. We have 2y, and we have x plus x plus y. That's our j component. And finally, we have 2y, and we have xz for our k component. So the derivative of x plus y with respect to y is just 1. Derivative of xz with respect to z is actually x. So we end up with an x plus 1. Sorry, not plus. We are subtracting those two. So actually, we'd have a 1 for this direction, but then we subtract the x from that direction. So that's our I component. This one, derivative of x plus y with respect to x, is 1. But then there's no z's in 2y, so the derivative with respect to z is 0. So we end up just getting a 1. So we have a minus j. Finally, derivative of xz with respect to x is z. Subtract the derivative of 2y with respect to y, which is 2. That's our k component. And so our line integral over that curve of f dot dr is going to equal the surface integral over our, I already said it was going to be our plane. Technically, we could use a different surface if we wanted to, but the plane is the one they kind of already gave to us in our picture. We had to come up with something completely different if we wanted to use a different surface. Of course, the plane is probably pretty simple as well. And of course, the plane also is a graph. It is the graph z equals y plus 2. The only difference here is that when we take the integral over our base, instead of being a triangle, is just the circle x squared plus y squared equals 1. So we're integrating over that disk. Remember, we're doing minus p. So p here is from our curl. So 1 minus x times the derivative of z with respect to y. With respect to x. We do x first. But the derivative of y plus 2 is 0. Then we subtract our j component of our curl, which is negative 1, times the derivative of z with respect to y. That, in this case, is a 1. Finally, we just add the last component of our curl. We have a z minus 2, though really not z minus 2, because we do want this to be, we're integrating over something in the xy plane. We need to replace z with y plus 2. So we end up with a y plus 2, then minus 2. Of course, those will cancel each other out pretty handily. Also, since we are integrating over the disk of radius 1, we could go ahead and use polar coordinates. We're going over the entire disk, which means that theta is going to go from 0 to 2 pi. R is going to go from 0 to 1 because the radius of our disk is 1. This part here, this part, I guess, go ahead and cross that out because of the 0 there. It's just a 0. This is a plus 1, and we have a y. We have y plus 1, essentially. Y in polar coordinates is r sine theta. 1, of course, is still 1. But we do need to multiply by an r dr d theta, because whenever we use polar coordinates, we have to put in the r. When we integrate with respect to r, keep in mind this r with that r becomes an r squared. So r squared, when we integrate it, we get a 1/3 r cubed. Doesn't affect the sine of theta, though. Then we have a plus r. Integral of that is a plus 1/2 r squared. When we plug in 1, we have just a 1/3 sine theta. And here we have a plus 1/2. And of course, when we plug in 0, everything becomes 0. Finally, we get to integrate with respect to theta. Integral of sine is a negative cosine. Integral of 1/2 is 1/2 theta from 0 to 2 pi. When we plug in 2 pi, cosine of theta is 1. So we have a negative 1/3. But when we plug in 0, cosine of 0 is also 1. So we'll end up subtracting a negative 1/3. In other words, we have a 1/3 here, but then we'll also be subtracting a negative 1/3 here. When we plug in 2 pi, this actually becomes a pi, but when we plug in 0, we get a 0. So those negative 1/3 cancel out. We're just left with a pi. And that is the integral of that vector field over that ellipse. Our next example, we're actually going to be taking a step back in our numbers. So after 10, we're going to 5. Here we're going to use Stokes' theorem to evaluate the surface integral of a curl. So that's not necessarily saying that we're going to be integrating over the curve, but I want to point out something that Stokes' theorem allows us to do. One of the big advantages of Stokes' theorem is that if a surface is very annoying to integrate over, it may be possible to switch to an easier surface. So if S1 and S2 have the same boundary, C, and we're integrating a curl over that surface, then the surface integral over S1 of that curl, well, that's just the line integral of the original f over that boundary curve by Stokes' theorem. But Stokes' theorem also says that we can integrate the curl over the other surface, S2, and it's also going to equal that line integral. These two integrals of the curl are equal to each other. In fact, that's a very useful fact, at least as long as you know what vector field you're working with is the curl of another vector field, which is not always going to be the case. We actually looked at some vector fields that were not that way before. Remember, one thing that would have to be true is that the divergence of the curl, remember the divergence of a curl is just the zero scalar, actually. So this won't necessarily work for every vector field, but if a vector field is the curl of another vector field, then it really doesn't matter which surface we pick as long as we have the same boundary curve. And that's important here, because if you actually look at what surface we're looking at most of a cube. Not the entire cube, but most of the cube. So let's go ahead and actually plot that cube. So we've got a lot of different points. They're the points where we have plus or minus 1 as our coordinates in every combination that we have. So all 8 different points of our cube. We can go ahead and actually plot the faces. So let's say we have that face. And why did you plot another point? I didn't want that. There you go. There we go. There's our cube. Now notice I did not actually put in the last face down on the bottom, because that's our surface, remember, is the top and four sides, but not the bottom of the cube. And it says oriented upward, meaning that we're going to actually use the upward orientation for the top surface. The other ones actually, because they have to be normal, and they have to agree with that orientation on the top surface, are the ones going to be pointing outward. Now, of course, if we wanted to take the surface integral over this entire thing directly, this would be 5 different surface integrals, each of which is not that complicated of an actual surface to work with. They are parallel to the coordinate planes, and so they'd actually be relatively easy to work with, but it's still 5 different integrals. Let's do this in one. Basically, if I were to think about the last side of this cube that I didn't plot in here, that would be another surface. It'd be another surface where the boundary of that surface would be this bottom square. But that bottom square is actually the boundary of this entire top, all 5 of these put together. These other lines that I have drawn in here are not part of the boundary, because they're actually in the middle of the surface. The boundary is this bottom square, and a much simpler surface would just be the square itself. They fill in the square at the bottom. And so by Stokes' theorem, and what we just talked about here, as long as we have the same boundary and we're integrating the curl, which we are, that's what they want us to do, then those 2 integrals have to be the same thing. I'm going to call that surface S, or I guess let's call the, they did name the surface. The surface that involves the other sides of the cube is going to be S. But if I look only at that last face of our cube, I'm going to call that S1. Just be different from S. And we're still going to go ahead and integrate that curl. Now, we are going to have to figure out what that curl is. And one thing that we do need to be careful about here as well, and this might not be so obvious, we have to pay attention to orientations. The fact that the top of the cube is all oriented outwards does not mean that we're also going to orient our last plane down here, our last face, as outwards as well. We're not going to be taking the downward orientation. We are actually going to need to keep that upward orientation, because we have to respect the positive orientation around our boundary. So as long as we're taking that upward orientation, that means our boundary is being followed in a counterclockwise direction. That means on this bottom face, we're still going to have to keep that same orientation on the boundary, which means that we need to take the upward orientation still. Otherwise, this would not be equal. So let's take that curl. That's the next thing we need to do. We need to take the curl of this function here, of this vector field. So we have x, y, z. We have x, y. We have x squared y, z. We have an x, y, z. We have an x, y. That's times I. What am I doing? I'm completely messing this up. That should be yz, which means I need the different ones. Sorry about that. I guess I kind of lost my train of thought there. We have then we have derivative with respect to x and z. That'll be an x, y, z, and x squared y, z. It's going to be our j component. Then we have x y. So this one is actually the way I wrote the first one. So we have x, y, z, and x, y. That's our k component. All right, the derivative of x squared y z with respect to y is going to be an x squared z. Derivative with respect to z of xy is actually 0. So that is our I component is x squared z. Here, the derivative of x squared yz with respect to x is 2xyz. Derivative with respect to z of xy, or xyz, is just going to be xy. I'm actually going to go ahead and use the negative there to swap the order of those. So we'll have an xy minus 2xyz as our j component. In fact, yeah, well, okay, I'll leave it the way it is. Then the derivative with respect to x of xy is y. Derivative with respect to y of xyz is xz. That's our k component. Now, what are we going to be doing with this? How are we going to parameterize this bottom surface? How are we going to parameterize this thing? Well, keep in mind, all we're really doing there is setting r of xy equal to xi plus yj, well, not plus 0. I guess it's minus 1 times k. Because our k, all of our z values down here are negative 1. Our actual normal vector here is going to be a positive k. Remember, if we take the derivative of this with respect to x, we're going to get basically just I. If we take the derivative with respect to y, we get j. And j cross I, I cross j, we need that order, will give us the k. We need that upward orientation for that surface, like I mentioned before. And so that means our surface integral over S2 of our curl of f dot ds is going to be the integral from negative 1 to 1 and negative 1 to 1. So that those are what our x and y's are doing. They're going from negative 1 to 1 in both cases. We have the curl. Remember, the curl is given by this thing, dotted with our derivative, our orientation, our k that we have here. And that's actually pretty nice, because when we're doing that with k, remember the k has components of 0, 0, 1. That means whatever we have here is times 0 for our first component of the curl of f. Whatever we have for the second component of the curl of f is also being multiplied by 0. The only thing that's being multiplied by 1 is our z component, our third component. Our third component is y minus xz. Now, of course, z is negative 1. So we're going to go ahead and put y minus x times negative 1. Or just, basically this all comes down to the integral of x plus y. Because we have a positive x now, and this y, and everything else got zeroed out. So let's go ahead and just write that out. And now it's a fairly nice looking double integral. Nothing too complicated here. Integral with respect to y is going to be xy plus 1/2 y squared, going from negative 1 to 1. When we plug in 1, we're going to have an x plus 1/2. When we plug in negative 1 and subtract, we have x times negative 1, but subtracted, so a plus x. Then we have minus 1/2 of positive 1, so actually minus 1/2. The 1/2s actually cancel each other out. So we get the integral from negative 1 to 1 of 2x dx. The integral of 2x, of course, is x squared from negative 1 to 1. Plug in 1, we get 1. Plug in negative 1, we get 1, but we're subtracting it, and we get 0. So a lot of work just to get 0, but That's what they had for us. But the point here is not so much what the result is, but the fact that we can realize that we don't have to use the more complicated surface if we can use a simpler one. If we can see a simpler surface to use, why not use that? And for our last problem of this, we're going to do essentially the same thing. We've got a particular vector field. We want to integrate its curl over the surface, where the surface is part of the paraboloid, z equals 1 minus x squared minus y squared, that is above the xy plane. If we go ahead and plot that thing, we have this, which we're only looking at the part above the xy plane, so we'll go ahead and put that in there, and zoom in on the part that's actually relevant. So we're just looking at this tip, where we're looking at the surface above the xy plane. We're looking at for that surface. But we don't really have to deal with that surface. If we pay attention to what the boundary curve is, it's just going to be the circle, in fact the unit circle, in the xy plane. That's the boundary of that surface. Can we think of an easier surface to work with than this paraboloid? Well, how about the unit disk? How about the actual disk in the xy plane of x squared plus y squared is less than or equal to 1? We could integrate over that surface instead, and we get the same result. Because they're two surfaces with the same boundary curve, the only thing we have to pay attention to here is what orientation do we use. And since they want us to use the upward orientation for the paraboloid, we'll also use the upward orientation for our unit disk. So I'll go ahead and say that S2 is the, actually let's just say unit disk. In the xy plane. We do actually need to know what the curl of f is. They haven't told that to us, so we'll have to compute another curl. But by this point, hopefully you're getting used to the process. We're going to put our vector field as our last row. We have our derivatives with respect to x, y, and z. We have I, j, k. So we have a y squared xy. We derive with respect to y and z for our I component. We have x squared sine z and xy with a derivative with respect to x and z for our j component. We have x squared sine z and a y squared with derivative with respect to x and y for our k component. Going diagonally, we have an x minus 0, so actually just leave out that parentheses. We have x times I as our first component. Here we have a y. This time we do have something going the other way, but I'm going to use the negative to swamp the order. So we'll have plus the derivative of x squared sine z with respect to z is going to be an x squared cosine z. Then minus the other derivative, which we said was y. Finally, here, the derivative of y squared with respect to x is actually 0, so we won't even have that. And then the derivative with respect to y of x squared sine z is also 0. So we don't have a k, we just have this. The integral over s of our curl, of course, is the same as the integral over our unit disk, so S2. Maybe instead of even calling that S2, let's call it D. D for disk. Plus, it's a region in the xy plane, so why not? Of course, also I didn't mention here the fact that we are working with something in the xy plane does mean that our normal vector here is going to be k. It's the upward orientation for a region in the xy plane. That means we are going to take this vector here. Technically, the z we'd have to go ahead and replace with. Well, actually, I guess z is going to be replaced by 0, because in the unit disk we have z equals 0. So we'll have x squared times cosine of 0, which is 1, minus y times j. This vector is going to be dotted with our normal vector of k, and then we'd integrate it over over this disk, which we probably use polar coordinates for in general. But the nice thing here is there's no k in our curl. The fact that both these derivatives came out to be 0 was actually really beneficial to us, because when we take the dot product of something that doesn't involve k with k, we get 0. And so the integral of 0 is 0. Now, keep in mind, this worked because we had such a nice normal direction for our surface D. If we used the paraboloid, we would have a much more complicated normal direction. A normal direction that would involve x, y's, and potentially z's, but we'd also have to put everything into some sort of other parameters, some like u or v, or maybe using the fact that everything's nice and symmetric here, you might use something like r and theta or something like that. But the point is here, we simplified it quite a bit by even being able to not have to do any sort of parameterization, because we're using just the unit disk, but also our normal direction turned out to just cause everything to cancel out anyways. So essentially the point here is Stokes Theorem allows us to actually simplify a lot of work that might not have been as simple to begin with. And that's one of the main reasons that we like using these kind of theorems. Alright, so I'm going to leave this here. We have one final section. This one's over the divergence theorem. And it's going to be somewhat similar, though a little bit different from both the Green's theorem and Stokes theorem that we have covered by this point. So meet me in that last section, and we'll get to learn all about it.